In the Factorial example, I talked a lot about the stack, and that whole situation deserves a little bit more explanation. The stack is a region of memory. As I said previously, there's two places where we're storing data in our assembly programs. The easiest place to store data is in the registers, but there's only 16 registers, and we only get to use 14 of them, and so that's not a place where we can put all our data. So the other place we can put data is memory. Now, memory we can think of as being sort of a big array of bytes. There's quite a bit of it in a modern machine. On a 64-bit machine, the system is going to be claiming that you have 2 to the 48 bytes of memory. Even if we just think about how much physical memory you have as far as memory chips in the machine, we're talking about 8 or 16 gigabytes of memory. So this is a big range of space where we can put whatever we want in our assembly programs. The way we operate on memory is by doing loads and store instructions, where we have some value in a register and we're putting it into a location in memory based on having a numeric memory address, sort of like the array index into this big array of bytes, or a big array of 64-bit integers is probably the more sensible way to think about it, with loads and stores of registers on 64-bit machine. And then, so a store, we're writing a register to an address in memory. A load, we're reading a value from an address in memory into a register. On Intel-style assembly, every instruction can sort of have an implicit load or store as part of it. That's not necessarily how it works on other architectures. Loads and stores are separate from other instructions on so-called RISC, or reduced instruction set machines, but that's not how Intel works, because it's from the 70s. In any case, we've got this big sort of array of memory, and part of that array of memory we are calling the stack. And when the program starts up, we have this region of memory that's been allocated to our program by the operating system, or the sort of C language runtime, or however we're getting it. And when our code starts executing, things will have been set up so that we have the RSP register containing the address of the top of the stack. As our program executes, the stack will grow down, the number in RSP will go down, and that will allocate more space for us to use on the stack. Now, we have a sort of simple example. We can go ahead and talk about how the factorial example works. So let's think about doing factorial of 2 and the recursive implementation as we just built it. So when we're going to do the allocating x on the stack version, because that's a nice clean way to think about this. So we're going to call factorial of 2. 2 comes in RDI. We're going to then do a enter 16 0. When we do that enter 16 0 instruction, what that means is that we are going to save the value of RSP. So we save the value of RSP by copying it into RBP. So there's 2 registers here. We have RSP and RBP. But RBP is also a safe register. So before we can save the value of RSP, we have to go ahead and push the old value of RBP onto the stack. Old RBP goes at the top of the stack. So that's going to cause RSP to end up here. Now, RBP is going to be made to point the value of RSP. And then we're requesting 16 bytes. So at this point, we're going to have RSP point here and RB RBP points here. So we've executed our enter 16.0 instruction, and what that did is it saved the old value of RBP onto the stack. It saved the old value of RSP into RBP, so RBP is now pointing to the top of the region of the stack that is allocated for this function. And we have 16 bytes in here allocated for our local variables. So there's space for 2 local variables, and one of them is going to get written with the value of 2, and I'll even put in x equals 2, because that's where x is going on the stack if we allocate x on the stack. Now there's one other thing that's important in here. That is, before our function even starts executing, the call instruction, the instruction that called us, because someone said call fact, that pushed the return address onto the stack. So before the call instruction, the stack pointer was pointing there. The call instruction pushed one thing onto the stack. The enter instruction pushed another thing onto the stack. Then we requested the allocation of some multiple of 16 bytes of memory for local variables. So that was 16 bytes. And so the total amount of space that we ended up extending the stack down by here was 32 bytes. And that is maintaining this 16-byte alignment requirement that we needed to deal with. All right, so once we've done all this, we say enter, then we do some stuff, and then we're going to call fact with x minus 1. And so let's go ahead and do that. We're going to call fact. So the call instruction is going to push a return address on the stack. The enter instruction is going to push a old RBP onto the stack. The enter instruction is going to allocate 16 bytes, the bottom half of which is going to be x equals 1. And I'm going to go ahead and number these as RBP 0 and RSP 0, because those are where the those two variables are during the execution of the body of the first call to factorial of 2. You know, if I make those 2's, that might be more convenient. And then we can go ahead and call this one RBP sub 1, and then this is RSP sub 1. So factorial of 1 is going to go ahead and return 1. So when we return 1, we're going to result in having, we're going to do our multiplication here in the dot, dot, dot. We don't really care about that. But when we call leave, the return value of this function is going to be here. So this again is the outer call to factorial of 2. In the inner call of factorial of 2, we also get to leave ret. So let's go through what happens there. So we have the stack with RSP pointing at the lowest point it goes to, RBP points to the old value. So when we leave, what that's going to do is it's going to restore the old value of RSP. So we're going to move the value of RBP into RSP. Then we are going to and we're going to pop the value off the stack. So to make that make sense, this has to go here. That makes more sense. So RBP and RSP are bracketing the local variables for each call to a function. So when we leave in the inner call, that's going to move RSP up here. Then we can pop RBP off the stack, which brings it back up here. Then when we call ret, we're going to pop this return address off the stack, which results in leaving the stack pointer here. And then we can continue going. Of course, the thing that we use the return address for is the return instruction in addition to popping the address off the stack, it jumps back to the location. So ret is a jump to here from the inner call, and also pops that address off the stack to leave the thing that we want. So that is basically how the stack works. I hope that wasn't horribly unclear, but this is the sequence that we end up with a call to factorial of 2. And in the two calls that we had, factorial of 2 and factorial of 1, this is where the stack pointer and base pointer pointed while we were in the body of those functions, executing the body of those functions. So that's the first stack example I want to give. There's one more thing that I want to talk about, though, while we're talking about the stack, and that is how command line arguments work in C programs. And one thing that we're doing here, which is important to keep in mind, is that we're talking about assembly programming, but the context that we're talking about assembly programming in is how a C program written for Linux looks as an assembly program. When the C program is compiled to assembly, what sort of thing is the assembly doing? So when we're talking about command line arguments in assembly, what we mean is, what does it look like from assembly when we pass command line arguments to a C program under Linux? So in a C program under Linux, execution starts at the main function, and it's int main, int argc, char pointer, argv array. So we have two arguments here to main, and according to the calling conventions, we know that argc is going to be in RDI, and argv is going to be in RSI. Now, my handwriting aside, the way argc works is pretty simple. Argc is just an int. Now it's an int, not a double, so it's possible that we really are storing it in EDI, not RDI, because we want a 32-bit integer value, but we're just going to say argument 1 goes in RDI. But we're just storing the number of arguments that are passed to the program in there. What's going on over here is a little bit more complicated, because this is a char pointer array. And an important thing to keep in mind about C, and something that I'm immediately going to do to make this a little bit clearer, is that when we're talking about an array being passed to a function, or an array of unknown size as a type, an array is just a pointer. The way we represent arrays is as the memory address of the first element in the array. And so without changing how this works at all, I can rewrite this from being a char pointer array to being a char pointer pointer. And that'll make the layout a little bit clearer. That's the same exact thing. I didn't change anything. I just changed how we're writing it. So now this argv contains the address of the first element in an array, where the first element in the array is an address of the first element in an array of char. A string in C is a sequence of characters, an array of char. This is a sort of two-dimensional array. So this argv thing, RSI, points to a location in memory that is an array of pointers. Each thing here is a pointer, char pointer, so that's 8 bytes. A pointer is a memory address. So that's 8 bytes, that's 8 bytes, that's 8 bytes. We don't know how many of these there are, except that when we're actually trying to program, we do, because this number contains the length of this array. That's also a common thing that we see in C, is that arrays don't know their own length because they're just pointers to the beginning of the array. So if we want to pass an array to a function, we generally pass the size of the array as a second argument to the function. We get into structures in a little while. We'll see that another option is that we create a structure that packages the beginning of the array and the size together. That's the implementation of arrays in most other languages, is a structure like that. But in C, we don't use structures by default. That's too complicated. So we'll just go ahead and have a pointer to the beginning of the array and the size. Each thing here is going to be a pointer to a string. So let's give a concrete example here. If we have if we're running a program on the command line, so this is our shell prompt, and we're going to run our program prog, and then we're going to pass it some arguments. So our first argument is going to be cat, and our second argument is going to be buffalo. And so there's two arguments. So in this example, it turns out that for this example, argc is 3, because what actually ends up getting stored in the array is all of the things on the command line. So the 0th item in the array is going to be prog, the 1th item is going to be cat, and 2 is going to be buffalo. So this is index 0, 1, 2. And so this now is going to be the string. This is actually the string /prog. This is now the string cat. And this is now the string buffalo. Now, the way we write strings in C is as characters between double quotes, but just to be clear, the way that's represented in memory is as an array of bytes followed by a null terminator. So buffalo is B, U, F, F, A, L, O, followed by a null byte, which we can write as \0. So this is an array of 8-bit integers, where the first one is whatever the ASCII code for B is, the ASCII code for U, F, F, A, L, ASCII code for the lowercase letter O, and then the number 0, that's the ASCII code for null. So that's the memory layout of, well, this is sort of how this two-dimensional array with arguments in it works. Now, the reason why I'm talking about this in relation to the stack is because all of this contents is actually allocated on the stack above where we start execution of our program. So if we actually looked at our stack here, so actually let me keep that and erase everything else. So if we look at our stack, when we call our main function, it's just like it was with the other example. Main is not especially special. So at the beginning here, when our main starts, we're going to have RSP pointing to what we thought was the top of the stack, and then RBP is probably pointing somewhere up here, because we haven't called enter yet. But ignoring RBP for the moment, because that's not the point of what I'm trying to talk about, we have to store the arguments to this function. So before that, we have our return address, because someone just did call main. That's what just happened before this diagram, is someone said call main. So call main pushed to the return address, and that moved the stack pointer down to here. Above that, we're going to have, so this was, RDI and RSI had our two arrays in them. RDI is 3, and then RSI is going to point to an 8-byte value here. So that 8-byte value is the pointer to the array of bytes. So it's not actually there, it is probably there's a null pointer followed by the pointer to buffalo, cat, and prog. I'm running out of space. Let me try harder. So we have, on the stack here, we have buffalo, we have cat, and we have Prague as strings. These are different lengths. There's probably alignment requirements here that are going on. But here we have RSI, which is pointing to there. And then this says something like this. So all of that content is on the stack. All right, so that's all we need to cover about stack layout and layout of strings, at least for now. There'll probably be more. And I think I have another example. I'll be back in a minute.